Hello and welcome to the next of the lectures in this week 9 of this course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In this lecture, we will look at continuous models of fuzzy relational inference schemes, which will prepare the base to discuss continuous models that are obtainable from either the compositional rule of inference or the BKS inference scheme. So far, we have studied interpolativity through the lens of solvability of the corresponding fuzzy relational equations. In this lecture, we will look at an alternative perspective of interpolativity, which will enable us to look beyond these two relations, R check and R cap. We know a fuzzy inference system can be thought of as a mapping between fuzzy sets, and this will enable us to discuss what are proposed as continuous model of a given rule base in the literature, and we will also justify why that particular definition can be seen as relating the continuity of a fuzzy inference scheme. Of course, this will also highlight the role played by residuated lattices. Now, when we discuss interpolativity of FRIs, whether it's the compositional rule of inference or the Bangalore cohort subproduct, our basic assumption was we are in the realms of a residuated lattice. That means T is a left continuous T norm and IT is its corresponding residual implication. We have a set of if-then rules. We obtain the matrix Q as from the antecedents of these rules and the matrix P from the corresponding consequence of the rules. We knew that if we were discussing the solvability of this equation, Q sub T R is equal to P, where Q and P are fixed and R is to be found out, then we are essentially discussing the interpolativity of CRI, and we have seen that this has a solution, that an R exists if and only if this R cap, which is given as Q transpose in phi TP composition, is a solution. Of course, it can be shown that it is a maximal solution also. Similarly, in the case of BKS, if you are looking at the interpolativity of a BKS inference mechanism, then essentially it boils down to solving this fuzzy relational equation, and we know that it has a solution only if R check, as given like this, is a solution. Now, when we discussed the relationships between FRI and SBR, or the equivalence between theta and phi t, we have again seen the role played by these two relations. These are R cap and R check. For instance, if we consider CRI, while interpolativity is ensured by R cap, that for the theta to be equivalent to phi t, the inference from theta to be equal to that of phi t, and to be able to look at CRI itself as a similarity based reasoning scheme, what helped us was the R check relation. And in the case of BKS, again, the duality persists. That means R check helps in the interpolativity, while it is R cap that actually helps us to show that the inferences from both theta and phi t will be equal, and also that you could look at BKS as a similarity based reasoning scheme for an appropriate matching function and the other operations. Needless to state, we are in the realms of residuated lattices, which is a bounded lattice. It's an ordered commutative monoid with identity 1, and the star and the arrow operation are related by this adjoint property or the restitution property. In the case that we are considering, we are picking up values from this unit interval 0, 1. So essentially, if you pick a left continuous T norm, then immediately we get a supply of the residuated lattice. Now, for an FRI that we are considering within this ambit, in this context, all the operations, whether it is for the composition or for aggregating the rules or even making the relation from the rule, we are picking all the operations from the corresponding residuated lattice. Now, discussing interpolativity of an inference scheme was essentially boiled down to discussing the solvability of such an equation. Q at the rate of R is equal to P, where at the rate symbol stands for the composition. And what we have done is we have either taken the sub T composition or in phi T composition and seen that to ensure that this system is interpolative, we need to show that R cap or R check is a solution for this system. However, it was not known when R cap or R check itself will be a solution. That is where the work by Clavon stands out. He proposed this sufficiency condition which showed that if this is valid, then in the appropriate compositions that we consider, whether CRA or BKS, the corresponding relations of R cap or R check will indeed satisfy the relational equation. Now, what is interesting about this condition is it decoupled the relation from its interpolativity. For instance, all it asked was that the antecedent should be normal, and it related the antecedents of the rules with the consequence through some operations which are again taken from the residuated lattice. Note that this by implication is given like this. So we see here that the interpolativity of an FRI scheme can be thought of even beyond the relation R cap or R check, purely in terms of the antecedents and the consequence. So this gives us an avenue to think differently, and let's see how to look at interpolativity of an FRI from a different perspective. Now, if you look at the form of the FRI, we know there are only two things that are important: the composition and the final relation itself. Of course, they may be obtained from some operations performed on the rules, which are operations performed on the antecedents and consequence of the rules. However, if you look at it, typically this is what is called the adjoint function of an FRI, which is essentially characterized by the relation R and the composition, which is denoted by the symbol at the rate of. Now this is the final fuzzy inference mechanism that we have, so it can be looked at as a mapping from f of x to f of y. When we look at it that way, as a fuzzy mapping, if you ask the question, what is interpolativity here? Essentially it is this function, this adjoint function, taking the value bi at ai for every I. So the question naturally arose, why not consider any relation R that is interpolative as an admissible relation R? Of course, we are not getting out of the residuated lattice structure. Being within the residuated lattice structure, we would like to explore if there are other solutions, other relations are. Note that R cap or R check is just one solution which will ensure interpolativity, and it will also be a solution. But there exist other solutions to ensure interpolativity. Let's look at the by implication a little deeper before going any further. We can look at by implication itself as an equivalence relation. So now, by implication is given like this in terms of the infix notation, where the arrow stands for the residual implication coming from the residuated lattice. This is how it is defined: min of x implies y, comma y implies x. Now, if you define E of xy as x by implies y, clearly this E, looking at it as a relation on x cross x, we see that it is reflexive. Note that this is an R implication, which means we know that this implication has IP and OP. IP means x implies x is 1, and OP says that if x is less than or equal to y, if and only if x implies y is equal to 1. So x implies x is 1 is essentially E of xx, so it is reflexive. Clearly it is symmetric. Is it transitive? Is it T transitive? Yes, it is T transitive, because by residuum, as it is also called in the literature in residuated lattices, this by residuum or by implication also satisfies this property, which is essentially written in the language of T norms, where star is the corresponding T norm T here. We see that this essentially means it is T transitive. So that means this by residuum, when you use x by residuum y, it is essentially an equivalence relation, a star equivalence relation. Of course, once you have a relation on 0, 1, you can extend it to any to the space of fuzzy sets as follows. You can take the membership values and use the biresiduum on this, and then take the infimum over all of those such values. Well, there is one thing to be noted. This E is in fact strongly reflexive. What do you mean by this? E of xy is 1 if and only if x is equal to y. Clearly, if x is equal to y, we know that E of xy is 1. But E of xy is 1 if and only if it also implies x is equal to y. This is clear from the ordering property of the corresponding implication. For instance, if E of xy is equal to 1, this means x implies y, y implies y is equal to 1. Now this implies minimum of x implies y, y implies x is 1, which essentially means this quantity is equal to 1, this quantity is also equal to 1. But we know that from ordering property, if this is equal to 1, then this implies x is less than or equal to y, and this would imply y is less than or equal to x. Put together both imply that x is equal to y. So this relation E is strongly reflexive, a property that we will make use of again and again in our discussions later on. Now, given a seesaw rule base, we are looking at the adjoint function of an FRI as a mapping from f of x to f of y. Let's pick a y from the output domain y, and I can be anything from 1 to n, just an arbitrary index from this. Let's define this function delta of Ri. Note that this R is arbitrary, any R that we are using in the FRI to represent the rules. This I is fixed, y is fixed. So delta Ri of y is given as this. It is Bi of y, the membership value that y takes in the corresponding consequent of the ith rule, with the biresiduum of the output obtained from this adjoint function fr at the rate of when ai is being given as the input. So this will be a fuzzy set on y, the membership value of that fuzzy set at that particular y that we have chosen. So this is delta Ri. This is the function that we would like to introduce. Now in terms of this, note that for a fixed I, if for every y element of y, if we know that delta Ri of y is equal to 1, what does this mean? Note that delta Ri of y is dA of y at the rate of ai. Now, if you know that this is equal to 1, that means both these quantities are same. This quantity and this quantity are same. These are membership values. Now, if this happens for every y, then that means for every y, both these quantities are effectively same. This implies Bi is in fact equal to Fr at the rate of a. So now for every y, delta Ri of y is equal to 1 implies Fr at the rate of at ai is in fact equal to Bi. Now since this is equal to 1 for every y, we could also represent it like this. If we take the infimum, it will still be 1. So now we obtain this from here. Now in terms of this delta Ri function, we could write or rewrite the interpolativity of this adjoint function as follows. You can say the adjoint function of an FRI, Fr at the rate of, is interpolative if and only if the infimum over delta Ri of y is equal to 1 for every I. So now we have an alternate interpretation of interpolativity itself. Well, now that we have an alternative perspective of interpolativity of an FRI, all we have seen earlier is this, that if R is equal to R cap, then Fr circle T, supremum T, which is the adjoint function of an CRI, is interpolative. Similarly, if R is equal to R check, the adjoint function of the BKS inference mechanism, where the implication is the residual implication IT, it is interpolative. So now you see here, these are some sufficient conditions, and these specify an R to be of a particular type for it to be interpolative. But these are only sufficient conditions. That means there exist other relations R under which CRI or a BKS can well be interpolative. Now, let's look at what we understand by a continuous model of an FRI. Recall that given a CISO rule base, an alternative view of fuzzy inference mechanism itself is as follows. You could think of the system function that we are trying to approximate using this fuzzy inference system itself is a fuzzy mapping. That means you could think of it as phi tilde, which is a mapping between f of x to f of y. Now, given this view and a partition AI, we could think of the antecedents AI forming a partition on the input space X and phi tilde acting on AI to give the consequence BI. So the antecedents and consequence of the rule can be thought of as having been generated by the system function phi tilde, which itself is a mapping from f of x to f of y, and where AI, the antecedents, are pieces in a fuzzy partition of the input domain, and the consequence BI are the images of these AI under the function phi tilde. In that sense, we saw that interpolativity is finding a fuzzy inference mechanism or system whose corresponding function psi tilde approximates this phi tilde at these AIs, or is equal to this phi tilde at these AIs. That's how we looked at interpolativity of an FIM. Now, let's extend this view. So given this rule base, we want to look at a fuzzy inference system as a mapping between f of x to f of y. Now, these antecedent consequent pairs can be thought of as coming from the Cartesian product of the input and output domains of fuzzy sets. Given this, we could define psi tilde to be a continuous model for this rule base if and only if the following inequality is valid. Notice this, much like the condition proposed by Clavon for interpolativity, this condition is firstly an inequality and it relates the given input A to the antecedents of the rules and the obtained output of A with respect to psi tilde, that means the image of A under psi tilde, to the corresponding consequence. So now we are looking at continuity in terms of the points that have been given, these pairs of fuzzy points that we have been given. Now the question is, why should we consider this as the continuous model? Why this term continuity coming into picture? Now let's take a short detour to understand this. If you want to talk about continuity of mappings, then we need a structure, an analytical structure on the underlying set. Perhaps it could be a topological structure, or we need the concept of sequences and their convergence, or we could also have a metric. So now let's look at having metrics on the spaces of fuzzy sets. So what is a metric? A function D from x cross x to the non-negative reals, such that it satisfies three properties, that of indiscernibility, symmetry, and the triangle inequality. Now with respect to metric space, if you look at a function f, if you want to talk about continuity of this function, then we need metrics both on the domain and codomain. So let's consider x and y as the domain and codomain with metrics dx and dy respectively. We say a function f from x to y is continuous at a point x0 in x if for every epsilon greater than 0 there exists a delta which obviously depends on both x0 and epsilon, such that whenever dx of x0 is less than delta, this implies dy of f of x from f of x0 less than epsilon. All we are saying is if x is close enough to x0 within the distance or measure of delta, then the image of x under f should be close enough to the image of x0 under f. Now we are looking at psi tilde as a function from fx to fy. Let's define some metrics dx and dy on these spaces. So now we can define what is continuity. Say psi tilde is continuous at an a dash if for every epsilon greater than 0 there exists a delta which once again depends on a dash and epsilon, such that dx of a dash is less than delta. This implies dy of psi tilde a and psi tilde a dash is less than epsilon. Now this is a general definition of what we would mean as a continuous function psi tilde from fx to fy given the matrix dx and dy. However, we need metrics now on the spaces of fuzzy sets. Let's turn towards the additive generators of t-norms to see whether they can generate metrics for us. Recall, an additive generator of a t-norm, a continuous t-norm, is a function f from 0, 1 to 0, infinity, which is continuous, strictly decreasing, and f of 1 is 0. Using this, with this formula, we can get a t-norm tf. This tf is called the generated t-norm, and f is called the continuous additive generator of tf. Now we have not specified what the value of f of 0 is. However, we know that if f of 0 is infinity, then clearly this f pseudo inverse becomes actual inverse of f, and the tf is in fact a strict t-norm. Now what is interesting is, if we take such an additive generator of a strict t-norm, that is f of 0 is infinity, and consider the residuated lattice obtained from this generated t-norm. Note that this is continuous, tf is continuous, so it's left continuous. So definitely it will give rise to a residuated lattice structure on 0, 1. If you take this t-norm and generate the residuated lattice structure, then it is interesting to note the representation the y residuum has in this residuated lattice. X by implication y is given as f inverse of mod fx minus fy. Now why this representation? We will make use of this representation shortly. Let us define a function df from f of x cross f of x to the non-negative reals, where f is an additive generator of a strict t-norm, means f of 0 is infinity. And let's define the function df like this. df of a dash is supremum over x element of x mod of f of ax minus f of a dash x. Note that a of x and a dash of x, they take values in 0, 1, they are membership values. So this is a valid definition. What we can say is this df in fact is a metric on the set of fuzzy sets on X. Now this can be easily seen. The indiscernibility, because it is supremum, and supremum is 0, then we know that what we have these values inside on which we are taking the supremum, they are all non-negative because it's mod. Then every one of those values is going to be 0, and because of mod and strict decreasing or strict monotonicity and continuity of f, we see that a of x has to be equal to a dash of x. Similarly, symmetry is clear. The triangle inequality follows from the triangle inequality of the mod function. So on fx, df is a metric. Now why did we create this metric? Because we wanted to relate that equation which we call the continuous model, the equation or the inequality, if it is satisfied by a psi tilde, we said that psi tilde is a continuous model of the given rulebase. We want to relate it. Why do we use the term continuity or continuous model there? So we say this is the rule base given to us. We say psi tilde is a continuous model for this rule base. By definition, this is the inequality we expect, which relates the given input to the antecedents and the output obtained from psi tilde to the consequence of the corresponding rules. This is what we have defined as the continuous model for a given rule base. This we can show is actually equivalent to the following inequality. So what does it say? It says that this, whenever this happens, this is equivalent to the psi tilde of a, the output, the image of a, the given input a under psi tilde, it says is much closer to the corresponding bi, consequent bi, compared to how close the given input a itself is to the corresponding antecedent. So we insist the image of a is closer to bi, much closer to bi than a itself to that of the antecedent ai, as measured by this metric df. Now the proof is not very difficult. Let's look at this. Note that what we need to prove is we are given this infimum over x, a of x, a of x. This is less than or equal to infimum over y, bi of x by residuum psi tilde of a. So now this we need to show is in fact is equivalent to, as you can see, df is a metric. So this talks about some kind of continuity. In fact, you can look at it as one Lipschitz continuity at the points a, I, b, a. So now let's start with this inequality and slowly go towards this. Remember, we are looking at the operations coming from a residuated lattice, which is obtained from this generated strict T-norm, Tf, in which case we know the by implication has this kind of a representation. So let's substitute that here. That means given this, substituting, this is in fact equal to infimum over x, f inverse of mod f of a of x minus f of a of x mod, this is less than or equal to infimum over y, f inverse of mod f of b of x minus f of psi tilde of a. Now, note that f is strictly decreasing, strictly monotonic. It is also continuous. So this implies if we have infimum over some xi, then this essentially becomes supremum over xi. Now, what we have here is an inequality. So if you apply f on both sides, then the inequality also reverses. So now applying f on both sides, what we get is the infimum comes out as the supremum. So we get supremum over x element of x. F and f will get cancelled. Minus f of a of x is greater than or equal to, because this inequality will change, f is a decreasing function, supremum over y mod f of bi of y minus f of psi tilde a of y. Now clearly, if you look at it, this is essentially how you have defined df, this on a. So this is df of ai comma a greater than or equal to df of bi comma psi tilde of. And this is exactly what we wanted to prove. And now you see, and everywhere it is an equivalent statement that we have written. So it's a by implication. So you could go back from this step to the inequality here, which means we have shown that this inequality is in fact equivalent to this inequality, which tells us that this psi tilde is continuous at these points a, I, b, a. Now it kind of justifies why this inequality can be considered as the inequality capturing the continuity of a model at the given points, essentially given the rule base, considering ai comma bi pairs as the points at which we want the fuzzy inference mechanism itself, the corresponding function, system function, to be continuous. Well, now this was an arbitrary fuzzy inference mechanism, but we could also consider the adjoint function of an FRI. So that means we can say FR at the rate of is a continuous model for a given rule base if this inequality is valid with FR at the rate of in the place of psi tilde, and that's because of this. So now what we have are these. Given a rule base, we see we have an alternative interpretation of an interpolative model. So we say that the corresponding FRI, because this is the adjoint function of an FRI, is interpolative if and only if this is valid for every I. And similarly, we can say the adjoint function of an FRI, FR at the rate of, is a continuous model for a given rule base if this inequality is valid. Note that we have used the residuated lattice obtained from the generated strict T-norm only to show that this inequality can be looked at as can be related to the continuity of the adjoint function with respect to symmetry. It is only for that purpose that we have taken recourse to developing a metric, generating a metric from the generators of additive generators of T-norms, strict T-norms. Henceforth, star will only be any left continuous T-norm. We will not fix it as the generated T-norm. So we are generalizing it. It is only contextually to show the relationship between this inequality and the continuity of the adjoint function or the fuzzy inference mechanism that we are considering. We took the help of the metric derived from additive generators of strict T-norms. Henceforth, the residuated lattice that we considered will be general in the sense that we could consider any left continuous T-norm. Now, a quick recap of what we have discussed in this lecture. We looked at an alternative perspective of interpolativity and looking at psi tilde as mapping of fuzzy sets using cleverly designed metrics or the space of fuzzy sets. We have seen when a fuzzy inference mechanism can be thought of as a continuous model of a given rule base, and essentially that means the adjoint function of an FRI when it can be thought of as a continuous model of a given rule base. This is what we have seen in this lecture. In the next lecture, we'll look at how to obtain continuous models of adjoint functions corresponding to the compositional rule of inference and the Bangalore cohort subproduct. The topics covered in this lecture are predominantly picked up from this work of Perfiliev and Lemke. And we'll meet in the next lecture where we'll discuss continuous models of CRI in details. Glad you could join us for this lecture and hope to see you soon in the next lecture. Thank you again.